Welcome back, my favorite 3x students. We are knee-deep in similar triangles, but we're going to go a little off topic, but it does relate to our topic. We're going to talk about the angle bisector theorem. Now, it's not in your book per se, but we do use similar triangles to actually find a relationship with what happens with an angle bisector. Now, an angle bisector cuts this angle right in half. So that angle is congruent to that. So it can be sneakily seen in some triangles that I just have this random line going through an angle and say, oh, these two are congruent. Think angle bisector theorem. But there is a nice relationship with the side lengths, but it's not like the side lengths we've been matching before. It's not short, medium, long, so on and so forth. Okay? So the relationship for the angle bisector theorem is AD is to this AC as DB is to BC, or CB, whatever you want to call it. But notice that I'm not matching short to short, medium to long, and long to long. What I'm really doing, and I reluctantly say this, it's kind of like a tangent, that if I'm sitting at my angle, just like right triangles, if I take the opposite length and divide by the adjacent, kind of like TOA, opposite divided by adjacent, that's going to equal the ratio of opposite over adjacent. Now, you're never going to prove that this triangle is similar to this triangle. Okay, so don't even try it. Don't try and find some random angles. You do have one angle, that's nice. But you're not going to be saying, like, this is the long and I'm going to match it with this side. Okay, we always go opposite divided by adjacent and opposite divided by adjacent. Now, why we talk about this in the similarity unit is because of the proof of the angle bisector theorem that I'm going to actually want you to prove after I give you some helpful little hints here. Again, we got to get some relationships with these side lengths and these side lengths. So what I'm going to do is actually add an auxiliary line. I'm going to take out my compass tool, our handy dandy compass. And if you see, I'm going to place it right on this point B. I'm going to flip it. I'm going to open it all the way up to point D. Make it, try and get it as exact as possible. And it looks like it's sitting on D. And what I'm going to do is I'm going to do a little half circle in red. So let's go. Okay, and actually not even a semicircle. We'll just go until I intersect that angle bisector that I extended out that far. Now, as you can see, it did intersect. And why we use the compass, obviously, or hopefully obviously, is that we make a lot of nice relationships, specifically with a circle. Every point on that circle is equidistant for B. So, looky here. If I draw a line from this new intersection to B, just like that, and say it is connected, what can we say about that? We'll call this point E. Now, every point on this red line is equidistant from B. So E is equidistant to B, and think about what else is. Well, so is D. Well, those two lengths then are congruent. That's a pretty nice relationship. So what I want you to do is eventually I want you to get through the proof to show this relationship. So it's kind of like prove this, given this. Now, I'll give you that. You can start with these dots and you don't have to mention, we'll draw the circle, so on and so forth. Just start with this picture and see if you can start matching up those side lengths. Now, hopefully you see what kind of, I'm going to give you some helpful hints here. EBD, think about what type of triangle it is. But from there, you got a lot of lines that are intersecting, vertical angles, supplementary angles. So see if you can get AD is to AC as BD is to BC. So that's our first topic for tonight. And that's going to be the end of similarity of triangles. For now, we're going to talk about it a little more in class. But we're actually going to move on to investigation 2, or lesson 2. We have 3 similarity theorems so far. Side, 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 angle, side, and angle, angle. Now what we're going to talk about next is the congruency of triangles. And really the only difference between the similarity of triangles and congruence of triangles is all congruent triangles are similar triangles. But think about their scale factor. A congruent triangle has a scale factor of 1. Similar triangles can have different scale factors, but congruency theorems, scale factor is 1. So think about if I was given 3 sides. In one triangle, it's, I don't know, 3, 4, and 5. Maybe it's a right triangle. But if I have another triangle that's 3, 4, 5, I wonder if they're actually congruent. And it is true that if I'm given 3 sides that are congruent of 2 different triangles, both of those triangles are congruent. Now here's another one, side, angle, side. Side, angle, side is another congruency theorem. But angle, angle, is that enough to say that that is a congruency theorem? Well, think about if I have 2 angles and I want to make a triangle out of that. Well, here's one of them. I kind of extended the lines, there's another one. But if I have those same 2 angles, let's say I grab this one. Maybe not, I'll just redraw them. But I'm going to draw this one way over here. So we'll say these are pretty much the same angle, I can make them the same, but now if I extend the lines, those definitely are congruent. So what I have to think about is maybe I need a little piece or a little more information, a couple more pieces of information. Now it does work for similarity, angle, angle still does. These 2 triangles are similar, but they're not necessarily congruent. So what we go to is angle, angle actually splits off into 2 different congruency theorems. Now imagine those 2 different angles again, and I set this length, that green length. Now I could rotate this, flip this, whatever I do, as long as I have the angle, the side in between, and the angle. Think about if you could actually draw a different triangle. I challenge you to try it. That you have this length, the same between those 2 angles, and it actually does work that angle, side, angle is a congruency theorem. Right. Another one is actually a divergence off of this also is angle, angle, side. Same type of idea, except where our side is. We need 2 angles and then the side not in between those 2 angles to be congruent in 2 different triangles. And that's another congruency theorem. So for tonight, that's pretty much it for our theorems. We have 4 congruency theorems so far. We're going to have 5 eventually. But we have side, 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 angle, side. So those are the same in similarity and congruence. But angle, angle doesn't work for congruency. We need another piece of information that's to deal with the side. Either the side's in between the angle or it's outside the 2 angles. So let's see how we can actually use these towards a proof. This is a very basic proof that we're going to be using. And it brings up another property that we're going to talk about. But just like our statement reasons, start with my givens. AB is congruent to AC. That's given. And AD bisects BC. Now I'm going to not write that as a given because that gives me a piece of information. But whenever I have information, put it in your picture. Okay, AB is congruent to AC. And then they say AD bisects BC. And I want to think about what that gives me. Well, if it bisects it, it means this length is congruent to this length. But I don't write that as a given. I actually have a new statement. I say BD is congruent to DC, or CD, sorry. Let's put some numbers to these steps. And we have to think about it. It's not just given to us. I mean, they'd have to state it just like this if it was given. But I could say that's the definition of a midpoint. Or I could say definition of bisecting. Cuts it in half, get 2 congruent things. Now, I have to get to one of my congruency theorems. I have 2 sides. So that kind of narrows it down. I don't want to use these 2 because I don't have 2 sides, so I'm still a side, 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 or side, angle, side. Now, I could look for an angle. It would have to be B and C, but, you know, they look the same, but don't go by looks. So I got to think about, well, you know, is there another side that they have? And actually, AD. Let's look at AD. Is AD congruent to AD? Of course it is. It's the same length. Now what we call that is the reflexive property. Just like when you go in your mirror, you see yourself, you see your reflection. This is the reflexive property. So it's a shared side. The reflexive property can be used for shared angles, and we might have talked about this already, but it's important to know that anything for congruency that's butt up against each other or it's overlapping, those are kind of those sneaky ones that we can slip in there for extra pieces of information to get your congruency. Now, when we write a congruency statement, guess what? Naming the triangles is just as important with similarity. So if I call it triangle BAD, bad, that's going to be congruent, not similar anymore, congruent to, well, I went single slash, triple slash, double. So I have to go triangle CAD by, well, I have three sides, the side, 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 congruency theorem. So as you can see, I have proven that those two triangles are congruent. Eventually, we're going to start talking about other parts. You might have heard of CP-CTC. I could say that and that, that, that. I get three more pieces of information, which is just awesome. I can maybe use that to new theorems, but for now, we're just talking about the congruency of those triangles. Good luck with that angle bisector theorem. We'll have more of these proofs inside of class with similarity and congruence, so have fun. Hopefully you enjoyed the shortened lesson tonight, but again, have fun. See you tomorrow.